Thanks, Jung. That was great. All right, yeah, I'm going to be telling you about some of the work I've been doing since I got here 5 years ago. I gave a talk like this for my job talk, but this is very much different, fortunately. Yeah, so the work I'm going to be talking about includes work by my group. I have pictures of Mark, you, Chris, and Renuka here. Mark was a postdoc that was working with me who now has a job in Zurich. And then the rest of my group is still here with me, but you is going to be graduating this spring. And then I also collaborate with a wide range of people across the world: Germany, Chile, UK, Australia, everywhere. So I'm going to start this talk out at the close to home, at the center of our own Milky Way. So if we look towards the constellation of Sagittarius, and we don't look at optical wavelengths, we look at infrared wavelengths, where the light can get through all of the dust that's between us and the center of our galaxy, we see this bright spot at the center of our galaxy. And that bright spot is an incredibly dense star cluster. Okay, this cluster and clusters like it in other galaxies are the densest stellar systems we know of in the universe. So the stellar density is about 10 million times higher at the center of our galaxy than it is where we are at 25,000 light years away from them. So between us and the nearest star, we'd have many millions of stars in this environment. Okay, it would be a very bright sky. So our story today is going to be about black holes, and so we're going to zoom right to the very center of that star cluster. And over the last 20 years or so, people have been making observations of the very center, the central tenth of a light year, which is just about 20,000 AU, so 20,000 times the Earth's sun distance, in our Milky Way. And that's what this movie is. It's a sequence of many, many, many observations taken over many years, showing the orbits of stars at the center of our galaxy. Okay? And if you look carefully, you can see that there are two orbits which have actually fully closed. So this yellow star right here goes all the way around, and it's closed its orbit. And this star right here is also closed its orbit. So these two stars are just moving in Keplerian motion, elliptical orbits, around some point at the center of our galaxy, this little star here in this image.
So that's time, right? So that means
yeah.
Their orbits are, their periods are like 10 years or so?
Yeah, that's right.
Amazing.
So that's because they're moving really, really fast. So they're moving at about 5,000 kilometers per second, or about 150 times faster than the Earth moves around the sun. Okay, so they're moving really fast, and that's because they're moving around something really massive, right? The amount of mass inferred at that point right there is 4 million solar masses. Okay, and so this is the evidence that there's a 4 million solar mass black hole at the center of our galaxy. There, in fact, is a little radio source at that position that is a very weakly accreting black hole. Okay. So that actually, the black hole at the center, the supermassive black hole at the center of our galaxy, that's what we call these big black holes, supermassive black holes, wasn't actually the first detection of a supermassive black hole. We first detected supermassive black holes in this paper by Martin Schmidt. This is on a radio source, 3C273, but he got an optical spectrum of this source and found out, based on its optical spectrum, that it had a large redshift, which in our expanding universe means that it's very far away from us. Okay? So it was one of the brightest radio sources in the sky, but yet it was actually the second most distant object known in the universe. It was about 2 billion light years away. Okay? And that meant that this object must be very luminous, and it was a point source, so it must be quite compact too. And over time, they actually realized that this source and other sources like it were variable on very short timescales, meaning these things had luminosities something like 10 times brighter than the brightest galaxy, but they were variable on very short timescales, meaning they must come from that luminosity must be coming from a very small region. These things are called quasars, and what we think they are We can never actually take an image like this, but what we think they are is gas falling onto a black hole eating up gas. And when that happens, the gas collapses into a disk due to its angular momentum. It heats up to temperatures of over 1 million degrees, and because of that, becomes extremely luminous. And sometimes there's radio jets that are launched to help get rid of the angular momentum. This is actually an image from the Hubble Space Telescope of that same quasar that was detected by Martin Schmidt. And if you very carefully try subtracting out the star, you can see that it's surrounded by some fuzz. And that fuzz is a galaxy, actually a really big galaxy. Okay? So this is a point source at the center of a galaxy that's brighter than that entire galaxy. And this was the first evidence that at the centers of galaxies, there are supermassive black holes. And through observations of those quasars, typically we find quasars really far away because that's where we think that black holes were growing the most. There was lots of gas stuff in the early universe. So if we look at the number of quasars far away, it's roughly equal to the number of galaxies, bright galaxies in the nearby universe. Okay? And so that led to the idea that, okay, there must be black holes sitting around in these present-day galaxies. Okay? But in the present day, most of these black holes aren't feeding. They're not accreting a bunch of gas because there's a lot less gas around. Most of it's been turned into stars or kicked out of the galaxies. And so we just see the galaxies with nothing at the center. But we can see the stars moving around that black hole. And that's what we're seeing in the Milky Way.
So even the center of Milky Way used to be a quasar?
Yeah, it was probably, at some point it was much brighter. Yeah. And we actually think even within the past few thousand years, or actually 300 years ago, we think there was actually a burst of activity where it was about 6 orders of magnitude brighter than it is now. So, yeah. But if it were a quasar, it would be something like 12 orders of magnitude brighter than it is now. Okay, so unlike the Milky Way, the Milky Way is really the only place where we can actually see individual stars orbiting around the black hole. And the reason for that is that if you take that 0.1 light year scale that we were looking at in that movie, and you put it at the distance of the nearest galaxy, it would be 1 pixel or less on our detectors. So this is actually a Hubble Space Telescope image of the center of Andromeda. Again, we see a dense star cluster. It's got a weird lopsided distribution. The way that we can find a black hole in this object is we can take all of the light from this red slit here, pass it through a grating or a prism to break the wavelength into a spectrum. That's what's shown over here. It's a spectrum. And these dark bands here are actually absorption lines from calcium in the atmospheres of stars in Andromeda. Okay? So it's not just one star, it's the collective light of many, many stars. And if you look right at the center here, you'll see that there's a little S right at the center there. Okay? And that is a Doppler shift. The stuff that's a little above the center of the galaxy, this is the center of the galaxy right here. The stuff that's above the center of the galaxy is blue shifted towards shorter wavelengths. It's moving towards us. Stuff below it is red shifted. It's moving a little bit away from us, and at quite rapid speeds. And right at the center, you'll notice it's not just your glasses, it looks a little fuzzy. Okay? The lines don't look as clear as they do up here. And the reason why for that is that right at the center, there's stars both moving rapidly towards us and away from us. Okay? And that means the velocity dispersion of those stars is very high, and we can characterize that from this spectrum. So it is rotating, but also we can measure not only the rotation, but we can measure the distribution of velocities along the line of sight. Okay? From the width of the line or the shape of the line. So the blurrier it is, the faster things are moving, right? So and actually the remarkable thing, I almost missed the punchline, is that from this data you can find out that there's a black hole that's 140 million solar masses. So something almost 2 orders of magnitude more massive than our own Milky Way. So pretty remarkable. So from measurements like this, in about 100 galaxies over the last 2 decades, people have found a relationship between the mass of the black holes at the centers of galaxies and the mass of the galaxies that they live in. And in fact, the measurement here is the overall random motions of the galaxy, the velocity dispersion. And you can see that the Milky Way here is actually is on the bottom left edge of this plot. Okay? Most of the galaxies where we have found black holes are galaxies that are more massive than the Milky Way. Okay. So that's fine, but in fact, most galaxies are significantly less massive than the Milky Way. So this is actually the number density of galaxies per cubic megaparsec versus their mass. This is the Milky Way. It's among the more massive galaxies that we know of in the universe. And if you go down an order of magnitude or two, you get a few or 5, 10 times the number of galaxies. So there are many more small galaxies than there are big galaxies in the universe. And yet, our measurement of black holes has been entirely in the most massive galaxies. And that's because these massive galaxies have really, really big black holes. You can see the black hole mass gets up to 10 to the 10 solar masses. That's almost the entire mass of the Milky Way. Okay? So those are easy to find. If there's black holes in these low-mass galaxies, they're not going to be so easy to find. Okay, but yet, I'm interested in this question. Okay? Do low-mass galaxies host black holes? That's the question that I've been working on for the last few years. There's been some history to this. In our local group, which is the nearest group of galaxies to us, we're all gravitationally bound together. There's a few galaxies that have been measured that have masses about 1 to 10% of the Milky Way's mass. And in only one of those galaxies have we found a black hole. The other two have very tight upper limits of about 10,000 solar masses on the upper limit on the mass of the black hole. So about 2 orders of magnitude less massive than the Milky Way's black hole. We can also try finding accreting black holes. So we can try finding black holes that are feeding at the present epoch. But that only is a very small fraction of galaxies. We found galaxies as low as about 10 to the 9 solar masses, which seem to be they're active galactic nuclei, AGN, which are basically scaled down quasars. Okay? And occasionally, stars stray too close to their central black holes. They're typically on kind of radial orbits, and they get actually tidally disrupted. And that tidal disruption ends up looking a lot like a supernova event. It's a transient event that lasts a time scale of about a month. And we've started finding those in plenty now, kind of as a result of trying to find supernovas to measure the distance scale of the universe. And in fact, the record holder has been, for the lowest mass galaxy known with a black hole, is from that kind of observation. But there's really no evidence for black holes in galaxies with the stellar masses below about 1 billion solar masses, which is about a 50th of the Milky Way's mass. Okay, so this is actually kind of the best summary of a set of observations trying to find X-ray sources at the centers of galaxies that are probably weakly accreting black holes. This is the fraction of the objects that have X-ray sources. So these data points are the fraction of objects that have X-ray sources as a function of the stellar mass of the galaxy. You can see for Milky Way mass galaxies, we detect X-ray sources in something like 80% of the galaxies. Okay? But as we go down to about 10 to the 9 solar masses, we don't see them anymore. And that's in part because the luminosity of these sources scales with the mass of the black hole. And so this gray region is some attempt to recover the fact that we're not able to detect those things, and to try suggesting that there's black holes. We reach a high fraction of black holes in galaxies somewhere around 10 to the 10 solar masses, and then somewhere below 10 to the 8 solar masses, we probably don't have any black holes at the centers of galaxies. So this is just kind of a model on some data. So the reason why this is an interesting question, whether these low-mass galaxies have black holes or not, is because one of the reasons is because we don't actually know how these supermassive black holes formed. Okay, so we see all these supermassive black holes in the universe. We know that they formed very early on in the universe because we can see them at very large distances. But we don't know what the initial mechanism was that formed these black holes. And low-mass galaxies, whether low-mass galaxies have black holes or not, these massive black holes at their centers, can tell us about what that mechanism is. It's, in fact, the only current observable that has the imprint of that process. And that's because if the process of making black holes was very common and abundant, the seeds for these present-day massive black holes was common and abundant, then we would expect all of the low-mass black holes, all of the low-mass galaxies to have black holes in them. Whereas in a rare, there's different real theoretical models here. This is actually, if the abundant low-mass seed model is that regular stars in the early universe that formed a little extra big because there was no metals leave behind stellar mass black holes, and those black holes grow over time. The high-mass seed is a special kind of mechanism where because there's so much gas in the early universe, you directly collapse to about a 10 to the 5, 100,000 solar mass black hole. That process is thought to be a lot rarer if it occurs at all. It's hard to model these things. And so you would expect very few black holes in low-mass galaxies because it's a rarer event. Okay?
Is that because there's not that much mass in those galaxies?
That's right. So the chance of, we actually think that galaxies form hierarchically. So they form little clumps, and then those little clumps merge to form big clumps. So you can think of big galaxies have many, many little clumps in them. So they're much more likely to end up with one of these seeds than a little galaxy. Okay? Okay, so that's one thing. If we can figure out what fraction of these low-mass galaxies have black holes, we can say something about the seed mechanism for forming these supermassive black holes. Another interesting fact is that in these low-mass galaxies, we expect to have black holes that should be below 1 million solar masses. And we actually know of basically no black holes between 62 and 10 to the 6 solar masses. Okay? That's 4 orders of magnitude. We have these objects that are, does everyone know what the 62 solar mass black hole is? That was the LIGO black hole that was detected this year, right? So that was a merging black hole, and it actually surprised everyone because it was more massive than any stellar mass black hole that we found. Both of the individual black holes were more massive than any stellar mass black hole we'd found before. And the combination, of course, makes it the most massive low mass black hole that we know of. And then there's this 4 order of magnitude gap, and we know lots of black holes that are above 10 to the 6 solar masses. Okay? There's actually been attempts to find these objects, and they've been very controversial. People have looked at the centers of globular clusters, trying to look at the orbits of individual stars, and lots of people have debated about whether they found black holes or not, and they've been claimed to be about 10 to the 4 solar masses. I've participated in some work to try getting very deep radio observations of these nearby globular clusters. Those have found stellar mass black holes in those globular clusters, but they haven't found any evidence for intermediate mass black holes. All we've been able to do is place upper limits based on the lack of radio detections at the centers of these globular clusters. There is one, in the entire universe, there's one object which we really think is about a 10 to the 4 solar mass black hole. And it's a very luminous X-ray source, off nuclear, so it's not at the center of a galaxy. It's off nuclear X-ray source around this galaxy that's quite far away from us. Okay, so answering this question of whether these intermediate mass black holes exist is an interesting one. So then we also want to know, we know that there's this correlation of black hole mass with galaxy mass, and in fact, I'm going to tell you that it's not quite with galaxy mass. But what you can see is that down here there just aren't any objects, and we don't know how this, by providing more lever arm on this relation, we can get a better sense of what the relation is. And I'm going to give you a little bit of galaxy anatomy so I can explain how this is different from the galaxy mass. So we have 2 kinds of galaxies in astronomy: elliptical and spiral galaxies. They were in that first picture, which I'm going to be showing you again with a little mystery later. But you can see there's a big galaxy here. It's an elliptical. This smaller galaxy is a spiral galaxy. Ellipticals and spiral galaxies have similar physical scales. They're 10 kiloparsecs, or 30,000 light years is kind of a typical scale. And at the centers of and at the center of spiral galaxies, we often have like little elliptical galaxies that we call bulges. Okay, and those bulges are pressure-supported, random motion stars with random motions, which is what we see in elliptical galaxies systems that are like mini elliptical galaxies at the centers of the spirals. And it's this mass, the mass of the elliptical galaxy or the bulge, that we think actually correlates most strongly with the black hole mass of a galaxy. And at the centers of both of these types of objects, we see these nuclear star clusters and black holes, and they typically have significantly less than 1%, normally about 1/10% of the total mass of the galaxy. So they're kind of gravitationally insignificant in the galaxy, except that right when you get really close to the center. Okay, so one of the things that's been interesting recently is that these scaling relations for a while were thought to be these perfect relations where you knew the galaxy mass, or actually the mass of the bulge of the galaxy, then you would get the black hole mass perfectly. And recently, we found that that's not the case. Especially if you look at spiral galaxies, there's a method of detecting black holes, which I'm not going to talk a lot about, but it's the most accurate method using disks of masers around the centers of galaxies. And from those maser galaxies, you can see if you just look at the blue dots here, there's at a given velocity dispersion or bulge mass, there's a huge scatter, a couple order of magnitude scatter in this relationship. And so I think this argues more that going down to lower masses and understanding what's happening here really will help us understand the demographics of black holes as a whole. Okay, so as I mentioned, detecting low mass black holes is hard because we need to find the motions of the stars within kind of the area where the black hole's gravity dominates. Okay, and so in a lower mass galaxy, you're going to have lower mass black holes, and you're going to have to look at a smaller area in order to find the black hole. And so in order to get high resolution observations, when we take a typical image even from a really nice place like Mauna Kea, this is Mauna Kea in Hawaii, the atmosphere blurs out our images. The lights twinkle, the stars twinkle a little bit, and that twinkling is the stars dancing around on our camera, and that'll make a big blurry circle, right? And we don't like that. That's crappy. So we want to get rid of that twinkling, okay? And the way that we do that is we shoot a laser, and we make a fake star right next to the object that we want to look at. And we look at that fake star and see how it's twinkling and try undoing the twinkle. So we pair it to a mirror that can be moved very rapidly with lots of pistons on the back of it and try undoing that twinkle, and that's called adaptive optics. And so that's the method that I've been using to get these observations. And this is actually the telescope Gemini that I've been using for that process. So I've been looking at some of the nearest galaxies, because that's our best chance for black hole detection. I'm going to be talking to you in detail about 2 of these objects. The other 4 of these red objects are objects that my grad student Yu is working on for his final paper of his thesis. And this is work that I've done in collaboration with Nadine Neumeier at in Max Planck Institute in Germany. Okay, so this first galaxy I'm going to talk about is a nearby galaxy. It's what's called a S0 galaxy. It's sort of in between a spiral and an elliptical galaxy. It's got very old stars, and it's also got some indication that it has an active galactic nucleus, very weakly active. So I wrote a paper on this before I came here, talking with trying to model using these kind of observations, the kinematic observations, trying to model the black hole, and I had some kind of mixed results. I had 2 different dynamical tracers. They gave 2 different answers, and it was a problem. But there's lots of evidence that there really is a black hole there. Okay, the source is variable right at the center. There's hard X-ray emission. There's radio emission. There's lots of things that wouldn't be there unless there's a black hole. So we think that there's a black hole there. It's just very hard to measure the mass of it. So the way that we try measuring the mass is we combine measurements of the kinematics of the stars, so the motions of the stars, that redshift and blue shift that I showed you earlier. That's what's shown up here. And also the motions along the line of sight. That's the velocity dispersion. That's what's on this bottom panel. So we can combine these observations, and the motions of the stars really tell us how much mass is there. The faster they're moving, the more mass has to be there, right?
Why is that?
Just from gravity. The more mass, the more massive an object is, the faster the circular velocity is, or the dispersion, or whatever. But then we can also take images of this galaxy, and we can estimate how much mass in stars is there based on those images. Okay, and so basically what we do is we compare those images, the distribution of light on those images, to the kinematics, to the motions of the stars, and we see, is there evidence for a component that isn't there in the light? Okay? And in general, the way that we find, what we really want is we want a model of the mass of the stars, but we can't just weigh the stars. What we can do is we can look at the image, we can assume that the stellar mass is distributed like the stellar light, and we generally actually assume a constant mass to light ratio, and that's what I had done in my initial study of this object. But we knew that wasn't a great assumption, because if you look at the center of this galaxy, so this is just the central 100 parsecs or so of this galaxy, these black contours are the nuclear star cluster. That's the brightness of the source. And the color here is really is a color. It's the ratio of how bright the object is in two different filters. Okay? And so what you can see is that the color of this varies within, really close to the black hole. And that's telling us that the stars have different ages and there's different stellar populations there. Okay? And so that means that for a given amount of light, we can't just say, oh, there's this amount of mass. We have to do something better. So that's what my student Yu's been working on. We got Hubble imaging and Hubble spectroscopy to take it, so that we got the spectroscopy along this white slit here. And rather than using the spectroscopy for measuring the motions of stars, here we tried using it to measure the stellar ages of the stars. And as stars age, we can characterize how much they should weigh per unit light. So we can measure their mass to light ratio. Okay, so from this, what this is showing here is here's our spectrum, and then this is a series of models of different ages of stars that add up to our spectrum, and we fit that. And we can fit it all along that slit to get a relationship between the color and how much mass is there. Okay, so we can transform this color profile into this luminosity profile into a mass profile using this relationship. Okay, you can see that redder things, this is redder things on this side, bluer things on this side. Redder things weigh more per unit light than bluer things. Yeah, Dima.
I have actually the same question that David had. So how do you distinguish something massive and these things flying far away from it, and something very light, but your things that you measure flying close to it? I mean, it is mass versus distance.
Yeah, so I mean, you know the physical, we know the distance to the object, so we know that what angular distance on the sky corresponds to the, so we know the physical distance on the sky here.
So you combine this Doppler shift with some other knowledge in order to.
Well, yeah, we need to know the distance to the object in order to find the.
From just Doppler shifts, you know it.
That's right. From just Doppler shifts, you wouldn't be able to do it. You need to know the distance, but you also need to know what the mass profile of the galaxy is, because you can model where in the galaxy that the light is coming from.
Do we know why red objects are more massive?
Yeah, I can, but it would take me a long time to explain. Okay, so what we can do is we can create models using the Jeans equation, which just links the gravitational potential to the motions of the stars, and so we can take that mass model that we have for the galaxy and predict, if there's no black hole there, what is the velocity profile going to look like. And what's plotted here is the speed of the stars. It's actually the rotation plus that random motion combined. And that's actually what the Jeans equation predicts. And so this bottom line here is what we would expect if there's no black hole there. Okay? And we can actually scale this, the height of that line is related to how heavy the stars are. If the stars are heavier than we assumed in our model, then that line would be higher. If they're lighter, then that line would be lower. Okay? And so we actually fit that. We can use this. You can see here there's different models with different black hole masses. And you can see very clearly this thing does not have a million solar mass black hole in it. Okay? This top line is clearly not obeyed by the data. Okay? And so we can fit for the best fitting black hole mass to light ratio, scaling, meaning how heavy the stars are. And then we also have to fit for the inclination of the anisotropy, which is, I won't get into, but we can marginalize over those parameters. And so this is actually a plot of the ratio of the dynamical to stellar population mass estimate. So this is about essentially how heavy the stars are on this axis. And this is the mass of the black hole. And this is the fit of the data to the model. And the models have been calculated in grids here. And you can see the white contours here are 1, 2, and then the red contour is 3 sigma for our best fit model. Okay, and then these 2 other models are some kind of systematic error analysis that we've done.
Would you learn something different if you weren't using optical wavelengths?
Yeah, so like if we looked at it in X-ray wavelengths or something. So the reason why optical wavelengths are good because stars shine at optical wavelengths, and stars are really bright. And so they have these absorption lines which we can use to measure the kinematics. At different wavelengths, you can, if you see that there's X-rays in the system, you can infer that there might be a high energy source there, but it's hard to actually prove that because there's different objects that can all. So for instance, accreting stellar mass black holes can also create X-rays. So this is the dynamical evidence is really considered the gold standard of finding black holes. So anyway, so you can see that these contours don't close on the left-hand side, right? And that means that we don't have a black hole mass measurement. We just have an upper limit. And our upper limit, though, is interesting. It's 2 times 10 to the 5 solar masses. This is the lowest mass black hole that we know of. We're pretty sure there's a black hole there because of all the X-ray and radio data. But we know that its mass is very, very low. Okay. So now I'm going to talk about another galaxy. This is a pretty spiral galaxy. And this galaxy is actually doesn't have a bulge component. So it's basically a pure disk galaxy. It doesn't have any hot pressure-supported component at the center. And this thing is actually also the nearest very active galaxy. So it's what's called a Seyfert galaxy. It has broad emission lines from gas spinning around the black hole very quickly. So this is the first bulgeless galaxy that we know of that has a black hole, and it kind of creates a problem because we think the black holes correlate with the bulge mass of the galaxy. So you'd expect a galaxy like this, under kind of a simple relationship, not to have a black hole at all. But it does, there's some discrepant mass estimates based on that accretion, the emission lines from accretion, and it's a kind of a difficult way to measure black hole masses. There's a lot of systematic effects, and there's 2 estimates that have been previously published which were differing by an order of magnitude.
So how do we know that the black hole in the year like 1989?
Yeah, so this was part of a survey they did of nearby galaxies. They got a nuclear spectrum, and they found that there was broad emission lines with a width of more than 1,000 kilometers per second. And that is, you really can't get, that's a surefire signature that there is a black hole there. So you can, this object actually, let me just say one more thing. This object spawned an effort to try finding similar objects in other galaxies, and it was spectacularly unsuccessful. They found like less than 1% of galaxies like this have black holes, but yet there's one just in our backyard. So it's kind of.
Any idea why it should vary that much from galaxy to galaxy?
It's just whether there's gas getting to the black hole at that current time. So you can imagine that gas sometimes falls into the center of a galaxy. That doesn't happen all the time.
So is this just a random phenomenon, or is there some?
No, it's probably not random. Yeah. There's probably reasons why some galaxies get gas or not. So this galaxy has gas around the center of it, and we can actually see that there's molecular gas that's emitting in the infrared wavelengths that we're measuring our source at, that we're getting spectra of. And this is actually showing the velocities, so you can see very clearly that it's rotating. This side is coming towards us, that side's going away from us. This is the velocity dispersion, and the point here is that it's very cold. It's got a very low velocity dispersion. So we think this thing is a disk that's rotating around the center of the galaxy and around the black hole. And we can use this just using the circular velocity, centripetal acceleration, and the circular velocity of the object to constrain the mass of the black hole and the mass of the stars in the cluster that surround it. And this is the measurements here. Again, we have 1 and 3 sigma limits. we get a best fit black hole mass of about 4 times 10 to the 5 solar masses. And this is the previous measurements. And you can see that we favor one considerably over the other one. So we have 2 black holes below 1 million solar masses that we have dynamical evidence for. So this is the end of the kind of the first part of the first set of results here. And basically we've started finding black holes down here that we can put on this diagram. And we've also started to constrain, and hopefully with Yu's thesis work, we'll really get a first measurement of what the occupation fraction is in galaxies at this low mass. Moving forward, I'm starting to use this Atacama Large Millimeter Array telescope, which is down in Chile at 16,000 feet. It's a millimeter wave observatory. It's fantastic, and currently has the best spatial resolution, the best resolution on the sky of any telescope that we can use, better than Hubble or better than the adaptive optic systems that I use. And at these wavelengths, what we can look for is cold carbon monoxide gas, which tends to be found in rotation in rotationally supported disks. We can use those rotationally supported disks just like we did in NGC 4395 to measure the black hole mass. And this is there's actually going to be our HEAP seminar speaker is someone who's working on visualization of this data on Friday. ALMA data in general, not just the data I'm working on. So the other thing is that I'm involved in a project, a Gemini large project. So Gemini is the telescope that I've been using to do all this work. And we recently had a project approved that was a very big project, basically a month on the telescope, to try measuring the black hole mass in about 30 galaxies. And here's pictures of a bunch of them. And the goal of this is to find galaxies. The galaxies that are known are in a very biased region of size and luminosity space. So green dots are all the galaxies that we have black holes measured in. The gray is where what the real galaxy distribution is. Okay, so the typical galaxies are bigger and less massive than the galaxies that we have measurements in. And we've tried finding all of the galaxies where we think, based on the existing scaling relations, we're going to be able to detect black holes. And that includes a few low-mass galaxies and also galaxies that are just kind of big at a given luminosity. And we're going to see what drives. This is going to help us understand black hole demographics. OK, so I'm going to finish the talk by talking about a kind of special object in this image. So this is an image of a nearby galaxy, Messier 60. It's a really big, giant elliptical galaxy. And it has one of the biggest black holes that we know of, a 4.5 billion solar mass black hole sitting at the center of it. Here's a spiral galaxy I mentioned. We don't actually know whether this thing has a black hole or not. But the object I'm going to talk about is this object right here. And this little dot is actually what we call an ultracompact dwarf galaxy. And this thing has a black hole that's 5 times the black hole mass, the supermassive black hole in our own galaxy. Okay? And so that's the Hubble Space Telescope image of that object. If we were to be a lot closer to that object, it would look something like this. This is actually the nucleus of a galaxy that's being eaten by the Milky Way. And you can see this is about 100 times less stars than are in this object. Okay, so this thing is an extremely dense, massive, compact object.
The stars are comparable size?
The stars are the same size as they are in our own galaxy. And, yeah, they don't change. So this is actually the real data that we get from the telescope. So this is from that Gemini telescope using the NIFS spectrograph. And this is at wavelengths of 2 microns. These absorption features we see here are actually they're carbon monoxide absorption features. And you can see at the center, these features are weaker and broader than they are further out in the galaxy. And that's because the motions along the line of sight are 102 kilometers per second at the center and only 50 kilometers per second in the outside. Okay? So this is actually, we can make a map because we have this we've done this adaptive optics. We're able to see what the motions are within this object, even though it only spans, it's like a dot almost on the sky. For most ground-based instruments, wouldn't be able to resolve it. but with adaptive optics we can. And you can see that it's clearly a rotating disk of stars. So these objects, this side is being blue shifted, this side is being red shifted. And the thing that got me really excited when I first got this data, I actually knew the result the very first day I got the data, is this red dot in the center here. That red dot is telling us that the stars right at the center are moving way faster than the stars just outside of that. Okay? So like the day I got this data, I actually had a model that we had put in the proposal, and I looked at it, and I knew that we had a big black hole sitting in this object. And so to weigh it, we need to, again, compare the motions of the stars to tell us how much mass is there, and compare it to the distribution of light that tells us what the distribution of stars is. Okay? And that in this object, unlike the other objects, we think that we can assume that the mass to light ratio is constant with radius. And that's because this thing is a very old system of stars. It's like a globular cluster. All the stars are about 13 billion years old. We can tell from its spectra. And also, the color map doesn't show any variations in this object. It looks uniform. So, so we used a somewhat more sophisticated modeling technique called Schwarzschild modeling. Ooh, there's a missing R there, sorry. You probably have heard of Schwarzschild before. So the Schwarzschild modeling is basically a method where you assume a potential, you populate that with orbits, and then you weigh those orbits to match your kinematics. And so it's kind of an iterative procedure, and it allows stars to have any possible physical orbits that exist in the system. So you really get a good assessment of the error bars on your measurement. And what you can see here is the 1, 2, and 3 sigma contours of the black hole mass versus the weight of the stars, the mass to light ratio of the stars. So that's how heavy the stars are. And you can see they're inversely correlated. If you have heavier stars, you get a lower black hole mass. Okay? And that's because the kinematics are what's forcing you to. There has to be the same amount. Well, not the same amount, but there has to be the total mass has to be kind of is not conserved, but you can trade out stellar mass for black hole mass. But a no black hole is actually a zero mass black hole is excluded at greater than 4 sigma. So we're pretty convinced there's a black hole here. This is a simple visualization of that modeling. Here's our data radially binned. It's the average speed of the stars at each radius. And this is the best fit model, is that black line. And the dashed line is the best fit model if there's no black hole. So you can see it's a pretty clear difference. You get this peak, that peak in the stellar velocity dispersion due to the presence of a black hole.
Does the black hole then cause the outer parts of the galaxy to be cooler?
No, it's just that, well, it does in a kind of, no, I mean.
The model is above the points there, the model with no black hole.
Yeah, so the reason why is that we've scaled this to best fit the data, okay. Right? But you could scale it down, and it would just go like this, and then you would just be seeing the effect of the black hole. Yeah. So this model has a higher mass to light ratio than that model. Yeah, good. So this is the lowest mass system that we know of that has a supermassive black hole in it, and that's from any kind of evidence. So this thing is, the stellar mass is about 1.2 times 10 to the 8th solar masses, so 120 million solar masses. And 15% of the mass of this object is in the black hole. Okay, so that's pretty remarkable, a pretty remarkable system. It's the highest mass fraction known. On this this is actually plotting the bulge mass now versus the black hole mass. This object falls way above that relationship. Okay. So compared to the Milky Way has about 0.01% of its total mass in a black hole. This object has 15% of its mass, and it's higher, even though it's a factor of 1,000 lower in stellar mass. Okay, so it's a very weird object, but we think there's actually a kind of a pretty easy to understand explanation for it, and that's shown here in this movie. So if we take a typical 10 to 10 solar mass elliptical galaxy, so slightly sub-Milky Way mass elliptical galaxy, and we throw it into this big giant galaxy that's sitting right next to this object, and it crosses close enough to the center, it has to cross within about a few thousand light years of the core of the galaxy, it'll get tidally disrupted. And the outer layers of it, and on every passage, more and more of the material will be stripped off. And over time, that material will kind of join with the envelope of the galaxy. but the core of the galaxy can survive. So what we think that this object is it's just that nuclear star cluster I showed you in that first picture of the Milky Way. It's like our Milky Way's nuclear star cluster with all of the other stars stripped away. And through the magic of simulations, you can have it at exactly the right place. Yeah, so it's about, the whole process is about a few hundred million years. The time scale is a few hundred million years. 500 million years, sorry. Yeah. So we actually think this process probably happened a long time ago, and that's why we don't see those arcs and shells of light, because over time those will dissipate into the galaxy. Yeah?
Are you looking at other ultracompact galaxies, dwarf galaxies, to see if you see the same? And maybe that's the way you explain.
Yes. Yes. So this is an exciting. The most exciting implication of this work is that there had already been some weird properties of ultracompact dwarf galaxies that have been noticed, and that's that if you took a spectrum of the whole object and you looked at what the motions were, their motions were faster than you'd expect based on how much stellar light was there and what their light distribution was like. Basically, if you weigh them with a single spectrum, you got too high a mass. And we kind of have a maximum mass that we expect from stellar populations in general. And if we look at like globular clusters, almost all of them that have decent measurements are below 1 on this graph. This is the weight relative to your expected maximum mass. But if you look at these ultra-compact dwarf galaxies, they're similar in size, but they're much more massive. They all weigh too much. And one of my collaborators, Stefan Miski, had published a paper in 2013 saying, that could be maybe the reason why this happens is that all of these galaxies have black holes of order 10% of the mass of their galaxy. And then we would misestimate their mass, and we'd think that their stars were heavier than they are. Okay? And so, in fact, for M60 UCD, which is this red point on this plot, it was slightly above 1 initially. And after we correct for the effect of the black hole, the stars are actually right in line with the globular clusters, the weight of the globular clusters. So if the stars weigh the same as the stars in globular clusters, which is what we'd expect. So this suggests that all of these objects might have high mass fraction black holes. And that turns out to be a lot of black holes. If we just look in nearby galaxy clusters, all these red and green points are UCDs, ultracompact dwarfs, and all the circles are dwarf galaxies. And it turns out that if we just take this indirect evidence for the inflated mass to light ratio as evidence that there really are black holes there, the number of black holes in these stripped galaxies is about the same as the number of black holes in the unstripped galaxies. Okay, so potentially doubling the number of black holes in the universe. Not the black hole mass, because these are all lower mass systems, and the black hole mass is dominated by the higher mass systems, but by number, maybe about half of the black holes in the universe. So of course, that's a pretty extreme claim, so we need to get more data. And so we've been doing that. Here's a night of observing, not my own night of observing, but a night of observing with the laser guide star on Mauna Kea. You can see the moon's up right now, so that's why it looks so bright. And then it gets dark. Anyway, so we've gotten data on more of these objects. Chris Ahn is working on this data as his first project. And he's found at least 2 more black holes, which is exciting. So here is the data. This is the speed of the stars as a function of radius. Here's the data. Here's the no black hole model. Here's the model with a black hole. And here's the cumulative likelihood after we marginalize over all of our other free parameters. Here's the cumulative likelihood of the black hole mass. So you can see the best fit black hole mass is about 6 times 10 to the 6 solar masses, 6 million solar masses. And the stellar mass is lower than, this is a less massive object than M60 UCD one was. And then we have one more where the evidence isn't quite as good, but still favors there being a black hole. Here, again, is the data is in the black points. Blue is the model with a black hole. Red is the model without a black hole. And here's the cumulative likelihood distribution. And there's all these lines are different systematic errors. And our 3 sigma is just barely above 0 here. So we think the best fit black hole mass here is 4 million solar masses. And that's about 10% of the total mass of the object. So in both of these cases, we do seem to find black holes. We have data on one more object, which is actually the brightest ultracompact dwarf galaxy known right now. And so we have very beautiful data on it, like we did for M60 UCD. And you can see, again, there's a red dot here. We just got HST data of this this summer. Chris is going to be working on it this fall and hopefully getting plots to show. So for the 3 objects that we've analyzed so far, all of them end up having the weights of the stars end up being normal. They're not inflated. And so that really does imply that all of these other objects here are UCD, are stripped galaxies that have high mass fraction black holes. And so I think you know, the total number of black holes that we end up with really depends on whether these objects, the less massive objects, which are more common, have black holes or not. And actually, my postdoc who's incoming is going to be working on these 2 objects in the triangles here when she comes, Karina Vogel. OK, so in conclusion, we can dynamically detect black holes in sub-Milky Way mass galaxies. Their demographics can tell us about the formation of massive black holes. And stripped galaxy nuclei do host black holes, and there might be a lot of those. I have one last slide, because the other thing that I've been doing since I've been here is working on this big survey of the Andromeda galaxy with the Hubble Space Telescope. It's been about 2 months looking at the Hubble Space Telescope in the first couple of years I was here. And I've been working with a bunch of people, Utah undergrads and postdocs, RU students, including Dylan Gregerson, Jordan Bulkeley, who are, Jordan's here, Dylan's finished, graduated, and also with a PhD student who I was the primary science advisor for, Cliff Johnson, who was at University of Washington. And he's published 4 papers on star clusters in this galaxy, including things like this beautiful object here. So this data that you're seeing here is from our Hubble Space Telescope imaging. You can see that the galaxy resolves into over 100 million stars that we've detected in the galaxy. OK, that's it.
You haven't mentioned dark matter.
Yeah. We don't actually think that dark matter, so dark matter can't dissipate at all. Like gas can dissipate and collapse down to the centers of galaxies and get really dense. So we don't actually think that dark matter probably, much dark matter ends up in black holes because the dark matter can't, if it's collisionless, it can't get dense enough to form black holes.
But it affects the revolutionary velocities of
Yes.
things
So
moving around, and you ignored that entirely.
yeah, so I have, and the reason why is related to exactly what I said. So the stars are probably formed from gas accreting into the center and forming a really dense stellar clump. We expect the dark matter to be dynamically undetectable within that radius. So you'd have to go to larger radii in galaxies to see it. And in general, within the central, you know, like half-light radius of galaxies, the amount of dark matter that is subdominant to the stellar mass. So it's only once you get out to kind of the Milky Way's, the sun's position in the Milky Way, that dark matter starts becoming really dynamically important.
What was the estimate for the mass of the galaxy prior to falling into the elliptical, the one?
About 10 to the 10 solar masses.
Okay.
So, but it was probably a elliptical galaxy because it's in a cluster. If for a 10 to the 10 solar mass elliptical galaxy, its black hole is actually a typical mass.
Okay.
So its bulge mass is 10 to the 10 solar masses then.
Okay. So because you had said that by looking at, you know, finding black holes in smaller galaxies that could tell you the seeding,
Yeah.
whether they're, you know, direct collapse or
Yeah.
stellar mass that accrete over time. So these objects, though, if they're all stripped galaxies,
Yeah.
then does that favor then still the idea that you have direct collapse?
So it's actually, if you look at this this graph right here, you can see the mass of the nucleus is probably correlates, or the mass with the UCD probably correlates with the mass of the host galaxy. And so this decline here could be either because could be that there's less black holes in galaxies that are less massive than the object that we're looking at. So you know, you can say, okay, this one's a 10 to the 10 solar mass galaxy here, a 10 to the 9 solar mass galaxy would be here, and that's where we kind of stop seeing black holes. So this would kind of support the idea that either black holes are not present in lower mass galaxies, or there's their lower mass fraction. They start having less mass relative to the mass of the nucleus and the galaxy as a whole. Yeah, so there is an angle on that demographic stuff, but it's hard.
I'm just curious, how does the distribution of stellar populations in an ultracompact dwarf galaxy compare to a globular cluster?
Okay. Yeah, so one of the differences is that there's a lot of stars. So in a globular cluster, there's few enough stars that they actually can dynamically interact. But in a ultracompact dwarf galaxy, they're unrelaxed systems, meaning the motions of the stars are only affected by the smooth potential and not by interactions with nearby stars. And so that means that that you don't expect to have any kind of say in a globular cluster, you can actually have mass segregation where like stellar mass black holes, the more massive things will collect near the center of the object because there's energy equipartition. There's energy is being shared between the different objects, and so because they are higher mass, they sink to the center. Okay, but we don't expect that to happen in UCD. So that's kind of that's important because it helps us it makes our interpretation more valid. Yeah. Otherwise, we could worry that there's just a bunch of compact objects sitting at the center of this object.
Is there any evidence for elliptical galaxies decomposing or changing into spiral galaxies, maybe because of interaction with other galaxies? Or is there any evidence in that?
Yeah, so it's exactly the opposite way. So Hubble thought that might be true. That's why he called them early type galaxies and called spiral galaxies late type and made his tuning fork diagram. But we actually think the opposite is true, that the stars form in disks because gas collapses due to its angular momentum. It collapses into disks. And so stars form in those disks, and the typical star formation sites are going to be spiral galaxies. But
Spiral galaxies become
but when two spiral galaxies merge together, their angular momentum aren't aligned anymore, and so they interact, and they'll create a bunch of random orbits with random directions, and you'll end up getting something that looks like an elliptical galaxy.
What is the timescale for this type of
So it would be hundreds of millions of years, yeah. So the orbital timescale of the sun around the Milky Way is a couple 100 million years, similar timescales. Yeah, Pierre.
So this is a bit of an unfair question.
That's fine.
But given how much our ideas about solar system formation have been disrupted in recent years by observation, what's the prospect for surprises?
Yeah, I mean, I don't think. I think there's been a lot of. For a long time, people were obsessed with is this thing in fact a black hole? Can we prove that it's dense enough to be a black hole? And that's pretty much been settled now. Really, the people. There's really very few people who believe that question is not settled. The density has to be so high, like in the Milky Way black hole and some of the other black holes we've detected, that you really can't have anything else. The galaxy formation stuff is becoming more and more of a settled topic, I guess, in the sense that we have simulations that can replicate our observations, and we have increasingly good observations out to very distant times. So I don't know. I guess I mean, it's kind of boring to say that there's not a whole lot of chance for surprise, but
I suppose the big difference is that you've been observing lots of different galaxies, whereas the solar system people until recently have only been observing one.
Yes, that's exactly that's a big difference. Yeah, yeah. Okay.
So first, like because this UCD is a galaxy, a lot of mass got stressed.
Yeah.
And so to basically learn about, for example, the formation of seed of this massive supermassive or we can go to low mass, we need to really go to field to observe this low mass galaxy, right?
Yeah. So I think for the demographics, it's probably more useful to look at the galaxies as they currently are because you don't have that extra uncertainty of what happened as the galaxy got stripped. But the one thing is that the black holes are a little easier to detect in the stripped galaxies because you don't have all of the layers of stars, the outer layers of stars. You don't have any star formation. So there's, I think the most likely place that we detect an intermediate mass black hole is in a globular cluster that was a stripped galaxy like Omega Cen or M54. And there's been evidence for both of those. Yeah. Does that answer your question? Or?
My second one is that, so this, I think that this scenario that's stripped, that's pretty convincing. So how about, the massive black hole in this bulge, this spiral galaxy?
Oh yeah. Well, so I think that probably the most likely thing is that I presented it as if there's just one seed formation mechanism. It's probably that there's a mix of seed formation mechanisms, that both of those things happen, and depending on which galaxy you're in, the seed was either a stellar mass black hole to begin with or a supermassive black hole. So I don't think that there's a correlation with the M-sigma relationship, but I don't think that if you think about it physically, that you would actually expect that to correlate down to infinitely small galaxies, because at some point you have to get down to where your seed was, and at that point you're not really the connection is thought to be related between the growth of the bulge and the growth of the black hole. So once you're at that kind of lower limit of whether there's a black hole there or not, you might just expect a plateau of black hole masses when they're present. Yeah. Yeah.
Take an ultracompact dwarf and a supermassive center.
Yeah.
And then you show the tidal forces, things nearby.
Yeah.
Does this talk about the end of that galaxy because of the accretion of the black hole?
Yeah. So eventually as galaxies merge together, there's this force called dynamical friction, which is that as this really massive object is passing through the envelope of the galaxy, stuff collects in its wake and acts as a drag force, and stars collect in its wake and act as a drag force. And that eventually will make this ultracompact dwarf in spiral to the center of the galaxy, and you'd expect it to merge with the black hole at the center and the cluster at the center of the galaxy. Yeah. So at some point that'll happen, and in fact, we can put constraints on what the orbit has to be in order for that not to have happened over the last 10 billion years or something. So it has to be very elliptical, otherwise it would have happened already.
And I was just wondering if you can get naming rights to individual stars in Andromeda Galaxy.
We haven't tried that as a Kickstarter campaign yet. But
Looks like be a good way to fund research.
You used a 3 sigma standard for your data significance.
Yeah.
Is that a standard in this kind of study, or where did it come from?
Yeah, I think in astronomy generally 3 sigma is where you can start claiming that you have a result. Of course, having higher significance is always better. But most people, that's what's considered the minimum publishable result, is I guess what I would say. Yeah, there's the problem with the black hole mass determinations is that there's a lot of systematic error that's hard to assess. So we've done our best, but that's a hard thing to assess. Yeah.
You talk of a phenomenon of pressure that's supporting this bulge at the center.
Yeah.
I don't get how these stars feel pressure.
Yeah, so that's kind of it's a typical velocity would be so the velocity dispersion of a system reflects how fast the stars are moving around, and you can think of that as you can equate it to the kinetic energy to a temperature, right? And so people call it like a pressure supported system as opposed to a rotationally supported system where your the primary motions are organized.
So how does this compare with the ideal gas law?
It doesn't, because there's no interactions between the stars.
Well, okay, they're not really bumping into.
They never bump into each other. Yeah, yeah. So you don't have a pressure in some sense. Yeah. Sorry, it's maybe a bad astronomer habit to say that.
I was upset by the idea of pressure.
Okay. Rest well.